Trade routes. These trails evolved into trade routes, connecting settlements and enabling commerce. Early civilizations. Ancient Mesopotamians and Egyptians built some of the first organized roads to support trade and large-scale construction, like transporting stones for pyramids. Challenges. These roads, while functional, were prone to erosion and impassable in bad weather. Roman engineering revolution. The Roman Empire transformed road construction with advanced techniques that remain influential today. Layered construction. Romans developed multi-layered roads using stones, sand, and gravel for durability. Drainage systems. Added drainage systems prevented flooding and erosion, ensuring long-term usability. Famous roads. The Appian Way connected cities, military outposts, and trade hubs efficiently. Legacy. Roman roads set a standard for infrastructure, with some still in use today. Medieval stagnation. After the fall of Rome, road building largely declined during the medieval era. Local roads. Roads became primarily local, connecting villages and farmlands. Poor maintenance. Roman roads were still used but had fallen into disrepair. Impact. Limited infrastructure hindered trade and economic growth, marking a period of stagnation in transportation development. The Industrial Revolution. The 18th and 19th centuries sparked a resurgence in road construction as industrialization demanded better transportation. Macadam roads. Invented by John Macadam, these roads used compacted layers of crushed stone for durability and smooth travel. Toll roads. Turnpikes emerged, where travelers paid fees to fund construction and maintenance. Urban paving. Cities began paving streets with cobblestones and later asphalt, improving urban mobility and commerce. Economic growth. Improved roads played a key role in facilitating industrial expansion and urbanization. Modern highways and smart roads. The 20th century revolutionized road construction with highways and technological advancements. Highway systems. Germany's Autobahn and the U.S. Interstate Highway System transformed long-distance travel. Materials. Asphalt and concrete offered smoother surfaces and enhanced durability. Smart roads. Modern innovations like solar-powered roads, embedded sensors, and infrastructure for autonomous vehicles are paving the way for sustainable and efficient transportation. Future trends. Advances in smart technologies continue to redefine how roads interact with vehicles and the environment. Conclusion. The evolution of roads demonstrates humanity's ingenuity and determination to connect and improve the world. From past to future, roads have grown from simple dirt paths to high-tech highways, shaping civilizations and economies. Next steps. With smart technology and sustainability at the forefront, the future of road engineering promises exciting innovations. Stay tuned to Blueprint to Reality as we explore more engineering marvels shaping the modern world. The importance of geometric design in roads. Welcome to Blueprint to Reality, the channel where we dive into the fascinating world of civil and structural engineering. From iconic structures to the science behind everyday designs, we break down complex concepts to show how engineering shapes our world. If you're passionate about learning the why and how behind what you see every day, you're in the right place. Introduction: the hidden science behind smooth roads. Have you ever wondered why some roads feel effortless to drive on, while others seem like a constant struggle? Behind the scenes, there's a precise science that ensures our roads are safe, efficient, and comfortable. This science is called geometric design, a discipline that balances safety, mobility, and functionality in road construction. Let's explore why geometric design is critical to modern transportation systems and how it impacts our daily lives.
What is geometric design?
Geometric design in roads involves the careful planning of a road's physical layout, including its curves, slopes, widths, and intersections. It's not just about aesthetics or convenience, but about creating roads that can handle various traffic loads, environmental conditions, and user needs. Every element of the design process is tailored to ensure roads are safe, efficient, and durable. For example, imagine a winding mountain road. If its curves are too sharp or its slopes too steep, the risk of accidents increases dramatically. Geometric design addresses such challenges by optimizing the road's alignment, grade, and other factors to suit the terrain and traffic conditions. Key elements of geometric design. 1. Alignment. Alignment refers to the road's horizontal and vertical layout. Horizontal alignment involves planning curves and straight sections, while vertical alignment focuses on elevations and gradients. Proper alignment ensures vehicles can travel smoothly and safely at recommended speeds, reducing risks such as rollover accidents or loss of control. 2. Cross-section. The cross-section of a road includes its lane widths, shoulder widths, and slope. Lane widths are designed to accommodate different types of vehicles, from cars to trucks, while shoulders provide space for emergencies and breakdowns. The road slope is critical for drainage, ensuring that rainwater flows off the surface and doesn't pool, which could lead to hydroplaning. 3. Sight distance. Sight distance is the length of road visible to a driver at any given time. It's a crucial factor in preventing accidents, as it allows drivers enough time to react to obstacles or changes in traffic flow. Poor sight distances, especially on curves or at intersections, are often linked to collisions. 4. Intersections and interchanges. Intersections are among the most accident-prone areas of any road network. Designing intersections involves careful consideration of factors like visibility, turning radii, and traffic control measures such as signals and signage. Well-designed intersections reduce confusion and improve traffic flow, enhancing overall safety and efficiency. The benefits of effective geometric design. 1. Enhance safety. Well-designed roads save lives. By minimizing sharp curves, blind spots, and poorly marked intersections, geometric design significantly reduces the likelihood of accidents. Research consistently shows that better road geometry leads to fewer collisions and injuries. 2. Improved traffic efficiency. Proper geometric design ensures steady traffic flow, reducing congestion and travel times. For urban areas, where delays can cost millions in lost productivity, efficient road layouts are essential. 3. Better driving comfort. A smooth, well-designed road isn't just safer, it's more comfortable to drive on. By reducing abrupt changes in elevation or sharp turns, geometric design ensures a pleasant driving experience. Environmental and economic considerations. 1. Environmental sustainability. Geometric design also takes environmental factors into account. Roads are often planned to work with the natural terrain, minimizing the need for extensive earthworks. This approach not only reduces construction costs but also preserves local ecosystems. 2. Cost savings. Properly designed roads require less maintenance over time. Features like effective drainage systems and stable slopes prevent issues such as flooding and erosion, which can damage infrastructure and lead to costly repairs. The future of geometric design. With advances in technology, geometric design is entering a new era. The rise of autonomous vehicles and smart cities is driving innovations in road planning. Future roads will be equipped with features like embedded sensors and communication systems that interact with automated vehicles. These roads will not only be safer and more efficient but also sustainable and adaptive to changing needs. For instance, highways designed for autonomous vehicles will have smoother alignments, fewer abrupt transitions, and features to facilitate vehicle-to-infrastructure communication. This will revolutionize how we think about road design and transportation. Conclusion: a foundation for modern society. The next time you drive on a perfectly smooth highway or navigate a well-designed intersection, take a moment to appreciate the incredible thought and precision that went into its creation. Geometric road design is not just an engineering challenge, it's a cornerstone of modern society. By ensuring roads are safe, efficient, and environmentally friendly, it plays a vital role in connecting people and places, shaping the way we live and travel. Thank you for joining us today. If you found this video insightful, make sure to like, share, and subscribe to our channel, Blueprint to Reality, where we break down the science and engineering behind the structures and systems that shape our world. Don't forget to hit the notification bell to stay updated on our latest videos.
See you next time.
The role of civil engineers in road construction. Welcome to Blueprint to Reality. Today, we're exploring a crucial topic: the role of civil engineers in road construction. Roads are more than just pathways. They are the arteries of our modern society, connecting people, goods, and services. Behind every mile of pavement lies the expertise and hard work of civil engineers. Let's uncover how they shape our transportation networks. Planning and design. Every road begins with a plan. Civil engineers are responsible for designing roads that meet both current and future needs. They assess factors like traffic volume, terrain, environmental impact, and safety. Using advanced tools such as computer-aided design, CAD, software, and traffic simulation models, engineers create layouts that determine road alignment, width, and the type of pavement to be used. They must also account for gradients, curves, and intersections to ensure smooth and safe traffic flow. Another critical part of the design phase is drainage planning. Engineers ensure that roads are equipped to handle water runoff, preventing flooding and erosion. Material selection and testing. The durability and performance of a road depend heavily on the materials used. Civil engineers select and test materials such as asphalt, concrete, aggregates, and soil. They ensure these materials meet specific standards for strength, flexibility, and longevity. For example, asphalt might be chosen for its flexibility in handling temperature changes, while concrete may be selected for areas with heavy traffic due to its strength. Engineers also evaluate subgrade soil to ensure it can support the road structure. If the soil is weak, they design methods to stabilize it. Construction supervision. Once the design is finalized, civil engineers oversee the construction process. They work closely with contractors and labor teams to ensure the project adheres to specifications and timelines. This includes supervising tasks like excavation, grading, laying the base and subbase layers, and finally, paving. Engineers also ensure the proper installation of road features such as curbs, signage, and guardrails. Quality control is a major part of this phase. Engineers perform on-site tests to check the compaction of soil, the thickness of asphalt layers, and the strength of concrete slabs. Their attention to detail ensures that the road will withstand traffic and environmental conditions. Safety and environmental considerations. Safety is at the forefront of every civil engineer's mind during road construction. Engineers design features like lighting, signage, and barriers to protect drivers and pedestrians. They also plan for emergency access routes and ensure compliance with safety standards. Environmental impact is another key consideration. Civil engineers work to minimize disruption to ecosystems by designing wildlife crossings, reducing noise pollution, and incorporating sustainable practices like recycling construction materials. Maintenance planning. A road's construction doesn't end once it's built. Civil engineers also play a vital role in maintenance planning. They assess wear and tear, monitor traffic loads, and schedule repairs to keep roads in good condition. From filling potholes to resurfacing pavement, engineers ensure that roads remain safe and efficient for years to come. Proactive maintenance reduces long-term costs and prevents major failures. Conclusion. The role of civil engineers in road construction is multifaceted and essential. From planning and design to construction and maintenance, they ensure that our roads are safe, durable, and efficient. Their expertise shapes the infrastructure we rely on every day. Thank you for joining us on Blueprint to Reality. If you found this video insightful, don't forget to like, share, and subscribe for more content on civil engineering and structural design. See you in the next episode. The science behind flexible and rigid pavements. Welcome to Blueprint to Reality. In today's video, we'll dive into a fundamental topic in civil engineering and road construction, the science behind flexible and rigid pavements. These two pavement types form the backbone of our transportation networks. But what makes them different? And how do engineers decide which to use? Let's break it down. What are flexible pavements? Flexible pavements, as the name suggests, are designed to flex under traffic loads. They consist of multiple layers, typically starting with a subgrade, followed by a subbase, a base course, and a surface layer made of asphalt. The primary characteristic of flexible pavements is their ability to distribute loads through a layered structure. When a vehicle moves over the pavement, the stress is highest at the surface and gradually decreases with depth. This layered structure allows the pavement to handle heavy loads while minimizing damage to the underlying soil. The key materials in flexible pavements include asphalt, which provides elasticity and resilience, and aggregates for strength and stability. One advantage of flexible pavements is their ability to adapt to minor settlements or deformations in the subgrade without cracking. What are rigid pavements? Rigid pavements are quite different. They are constructed using cement concrete slabs and rely on the inherent rigidity and strength of the material to distribute loads. Unlike flexible pavements, they do not flex under traffic loads, but instead spread the pressure over a larger area. The design of rigid pavements typically includes a concrete slab supported by a base or subbase layer. These pavements are known for their durability and long service life. Cracking is a potential issue, so they often include joints or reinforcements to control where and how cracks form. Rigid pavements are ideal for areas with heavy or repeated loading, such as highways, airports, and industrial zones. While they are more expensive to construct than flexible pavements, their reduced maintenance costs can make them a cost-effective option over time. Key differences and performance factors. Let's compare flexible and rigid pavements in terms of key performance factors. Load distribution. Flexible pavements distribute loads through multiple layers, while rigid pavements rely on the stiffness of the concrete slab. Material composition. Flexible pavements use asphalt, which is softer and more elastic, whereas rigid pavements are built with concrete, known for its compressive strength. Cost. Flexible pavements have a lower initial cost, but require more frequent maintenance. Rigid pavements, on the other hand, have higher upfront costs, but are more durable and need less maintenance. Lifespan. Rigid pavements can last 20 to 30 years or more, while flexible pavements typically last 10 to 15 years with proper upkeep. Suitability. Flexible pavements are preferred for roads with moderate traffic and regions with significant temperature variations. Rigid pavements are best for high-traffic areas and locations with stable climatic conditions. How engineers decide. Choosing between flexible and rigid pavements depends on several factors, including traffic volume, soil conditions, climate, and budget. Heavy traffic usually warrants rigid pavements. Poor subgrade conditions might favor flexible pavements due to their layered structure. Flexible pavements can adapt better to freeze-thaw cycles, while rigid pavements perform well in stable climates. Initial costs versus long-term maintenance considerations play a critical role. By analyzing these factors, engineers can select the most suitable pavement type to ensure safety, durability, and cost-effectiveness. Conclusion. Understanding the science behind flexible and rigid pavements helps us appreciate the thought and planning that go into building our roads. Whether it's the adaptability of flexible pavements or the strength of rigid ones, each type serves a unique purpose in modern infrastructure. Thank you for watching Blueprint to Reality. If you found this video helpful, don't forget to like, share, and subscribe for more insights into civil engineering and structural design. See you next time. The Science of Concrete Roads. Welcome to Blueprint to Reality. Today, we'll explore a topic fundamental to modern infrastructure: concrete roads. Concrete has been a trusted material for centuries, but its application in road construction offers unique advantages and challenges. What makes concrete roads so durable, and how do they compare to asphalt? Let's break it all down in this video. What are concrete roads? Concrete roads are built using a mixture of cement, water, sand, and aggregates. This combination undergoes a chemical process called hydration, where the cement hardens and binds the components into a solid mass. Concrete roads are often used in areas requiring long-lasting infrastructure, such as highways, industrial zones, and urban arterials. Unlike asphalt, which is more flexible, concrete is a rigid material designed to distribute loads evenly over the subgrade. Why choose concrete roads? Concrete roads are renowned for their durability and strength. Let's examine why they are preferred for certain applications. 1. Long lifespan. Concrete roads can last 30 to 50 years or more with proper maintenance, significantly outlasting asphalt roads. Their durability makes them ideal for high-traffic areas and heavy-duty applications. 2. Low maintenance. Concrete roads require less frequent repairs compared to asphalt. They are resistant to rutting, potholes, and surface deformation. 3. Strength under load. Concrete's rigidity allows it to handle heavy loads without significant deformation. It's especially useful in industrial zones with heavy truck traffic. 4. Environmental benefits. Concrete is made from abundant natural materials, and modern production methods have reduced its carbon footprint. Light-colored concrete reflects sunlight, reducing urban heat islands and lowering cooling costs. 5. Safety features. Concrete provides excellent skid resistance and visibility at night due to its lighter color. Its reflective surface reduces the need for extensive lighting on highways. The science behind concrete roads. Let's delve into the properties that make concrete roads unique. 1. Rigid pavement design. Unlike asphalt's flexible structure, concrete roads are built as rigid pavements. The load is distributed over a wide area, reducing stress on the subgrade. 2. Jointed and continuously reinforced designs. Concrete roads include joints to control cracking caused by thermal expansion and contraction. In some cases, steel reinforcement is used for added durability, creating continuously reinforced concrete pavements, CRCP. 3. High compressive strength. Concrete's ability to withstand heavy loads under compression is a key factor in its widespread use for roads. 4. Thermal behavior. Concrete expands and contracts with temperature changes, requiring careful design to prevent cracking. Applications of concrete roads. Concrete roads are versatile and find use in various scenarios. 1. Highways. Long-lasting and low maintenance. Concrete highways are ideal for intercity and cross-country travel. 2. Urban roads. Major city streets often use concrete for durability and ease of cleaning. 3. Industrial areas. In zones with heavy truck traffic, concrete can withstand the stress without significant wear. 4. Airport runways. Concrete's strength makes it a preferred material for runways, where aircraft impose substantial loads. Challenges of concrete roads. While concrete roads offer numerous advantages, they also come with challenges. High initial cost. The upfront cost of concrete roads is significantly higher than asphalt. Longer construction time. Concrete roads require more time to set and cure, leading to longer construction timelines. Limited flexibility. Unlike asphalt, concrete does not handle subgrade movement well, which can lead to cracking in certain conditions. Advancements in construction techniques and materials are addressing many of these challenges, making concrete roads more efficient and accessible. Concrete versus asphalt. Key differences. Here's a quick comparison between the two materials. 1. Durability. Concrete lasts longer but costs more upfront. 2. Maintenance. Concrete requires less frequent maintenance, but is harder to repair. 3. Flexibility. Asphalt is better for areas with frequent freeze-thaw cycles, while concrete thrives in stable conditions. Conclusion. Concrete roads are a testament to the strength and ingenuity of modern engineering. While they require careful planning and investment, their long-term benefits make them an invaluable part of transportation infrastructure. Thank you for joining us on Blueprint to Reality. If you found this video informative, please like, share, and subscribe for more insights into the science and design of civil engineering.
See you next time.
Sustainable road materials, a new era. Welcome to Blueprint to Reality, your trusted channel for exploring civil and structural engineering. Today, we're diving into the future of road construction and the exciting innovations in sustainable road materials. From recycled waste to bio-based products, these materials are paving the way for a greener and more efficient infrastructure. Let's explore this fascinating topic. 1. The need for sustainable road materials. As global infrastructure grows, the demand for road construction materials increases, leading to the depletion of natural resources and a rise in carbon emissions. Traditional materials like asphalt and concrete have a significant environmental footprint due to energy-intensive manufacturing processes. Sustainable road materials address these issues by reducing resource consumption, minimizing waste, and lowering greenhouse gas emissions. The shift toward sustainability is not just an environmental necessity, but also a step toward creating cost-effective, durable and innovative solutions for future roads. 2. Recycled waste in roads. One of the most promising trends is the use of recycled materials in road construction. Plastics, rubber tires, and even industrial waste like fly ash are being repurposed to replace or supplement traditional materials. For example, plastic waste can be melted and mixed with asphalt to create durable road surfaces that are resistant to cracking and wear. Similarly, crumb rubber from used tires improves flexibility and longevity in asphalt roads. These approaches not only reduce landfill waste, but also enhance the durability and performance of the roads. 3. Bio-based materials. Bio-based road materials, derived from renewable resources like plants and agricultural waste, are gaining attention for their sustainability and environmental benefits. For instance, lignin, a byproduct of the paper industry, can be used as a binder in asphalt, replacing petroleum-based products. Another example is the use of algae to produce bioasphalt, which offers similar performance to traditional asphalt while being biodegradable. These innovations not only reduce reliance on fossil fuels, but also promote the circular economy by repurposing waste into valuable resources. 4. Permeable pavements. Permeable pavements are an innovative solution that addresses urban flooding and water management challenges. These pavements are designed to allow water to pass through, reducing surface runoff and recharging groundwater. Made from sustainable materials like porous asphalt, concrete, or recycled aggregates, they help prevent waterlogging and reduce the urban heat island effect. While the initial cost of permeable pavements may be higher, their long-term benefits in water conservation and urban resilience make them a sustainable choice. 5. Self-healing materials. Self-healing road materials are a game-changer in reducing maintenance and extending the lifespan of roads. These materials are designed to repair minor cracks and damages autonomously, minimizing the need for frequent repairs. For example, asphalt mixed with microcapsules containing rejuvenators can release healing agents when cracks form, restoring the material's integrity. Similarly, concrete infused with bacteria that produce limestone can seal cracks upon contact with water. These innovations not only save costs but also reduce the environmental impact of road maintenance. 6. Local and renewable resources. Another approach to sustainability in road construction is the use of local and renewable resources. Utilizing locally sourced materials reduces the carbon footprint associated with transportation and promotes regional economies. Renewable resources, such as bamboo for reinforcement or coconut coir for stabilization, offer environmentally friendly alternatives that are often more affordable and accessible in certain regions. By incorporating these resources, road projects can achieve a balance between sustainability and practicality, especially in developing areas. 7. Challenges in adoption. Despite their benefits, sustainable road materials face challenges in adoption. High initial costs, lack of standardization, and limited awareness among stakeholders can slow their implementation. Additionally, large-scale production of bio-based or recycled materials may require advancements in technology and infrastructure. Overcoming these barriers will require collaboration among governments, industries, and researchers to promote innovation and create supportive policies for sustainable road construction. 8. The future of road materials. The future of sustainable road materials is promising, with advancements in research and technology driving new possibilities. Nanotechnology, for instance, is enabling the development of ultra-durable and energy-efficient road materials. Smart roads embedded with sensors and renewable energy systems are also becoming a reality. By investing in sustainable materials today, we can create infrastructure that is not only environmentally friendly but also resilient, adaptive, and cost-effective for generations to come. Sustainable road materials represent a new era in infrastructure development, combining innovation with environmental responsibility. By embracing these materials, we can reduce our ecological footprint and build roads that align with the principles of sustainability. If you found this topic insightful, don't forget to like, share, and subscribe to Blueprint to Reality for more explorations into the future of civil and structural engineering. Thanks for watching, and see you in the next video. The evolution of roads, from dirt paths to highways. Welcome to Blueprint to Reality, where we uncover the engineering marvels that shape our world. Today, we'll take you on a fascinating journey through the evolution of roads, from humble dirt paths to the complex highways that connect our lives. The origins of roads. Roads began as simple dirt trails created by early humans and animals to navigate their environment. Trade routes. These trails evolved into trade routes, connecting settlements and enabling commerce. Early civilizations. Ancient Mesopotamians and Egyptians built some of the first organized roads to support trade and large-scale construction, like transporting stones for pyramids. Challenges. These roads, while functional, were prone to erosion and impassable in bad weather. Roman engineering revolution. The Roman Empire transformed road construction with advanced techniques that remain influential today. Layered construction. Romans developed multi-layered roads using stones, sand, and gravel for durability. Drainage systems. Added drainage systems prevented flooding and erosion, ensuring long-term usability. Famous roads. The Appian Way connected cities, military outposts, and trade hubs efficiently. Legacy. Roman roads set a standard for infrastructure, with some still in use today. Medieval stagnation. After the fall of Rome, road building largely declined during the medieval era. Local roads. Roads became primarily local, connecting villages and farmlands. Poor maintenance. Roman roads were still used but had fallen into disrepair. Impact. Limited infrastructure hindered trade and economic growth, marking a period of stagnation in transportation development. The Industrial Revolution. The 18th and 19th centuries sparked a resurgence in road construction as industrialization demanded better transportation. Macadam roads. Invented by John Macadam, these roads used compacted layers of crushed stone for durability and smooth travel. Toll roads. Turnpikes emerged, where travelers paid fees to fund construction and maintenance. Urban paving. Cities began paving streets with cobblestones and later asphalt, improving urban mobility and commerce. Economic growth. Improved roads played a key role in facilitating industrial expansion and urbanization. Modern highways and smart roads. The 20th century revolutionized road construction with highways and technological advancements.